somewhere in the deepest dark, a galaxy is shining that should not exist yet. The universe was only 280 million years old, a newborn, too young for giant galaxies, too young for the elements that make planets and people. And yet, the James Webb Space Telescope found one, bright and heavy, and already full of oxygen. Then it found hundreds more. Tonight we travel to the edge of time. You will see tiny red dots that hide monster black holes, a giant spiral that grew up far too fast, and galaxies that died before they should have been born. If deep space mysteries pull you in, tap like and subscribe so you never miss one. The early universe was hiding something enormous. Let us go and find it. On Christmas morning in 2021, a rocket climbed into the sky, carrying the most expensive machine humans had ever launched. Folded inside its shell sat a giant mirror, packed tight like origami, waiting to bloom in the cold of space. This was the James Webb Space Telescope. Scientists had spent 30 years building it. $10 billion, millions of hours of work. And for the first few weeks, nobody knew if it would survive. The telescope flew almost 1 million miles from Earth. That is 4 times farther away than the moon. Out there, in deep shadow, it opened its golden mirror, one panel at a time. That mirror stretches more than 21 feet across, wide enough for a grown adult to lie down on it and still have room to spare. Every piece had to lock into place perfectly. One jammed motor, and the whole mission would die in the dark. So why build something so huge, so far, so risky? The answer hides in the kind of light this telescope was born to catch. Your eyes see visible light, red, orange, yellow, every color in a rainbow. The famous Hubble telescope mostly saw that same light, and it gave us stunning pictures for 30 years. But Hubble slammed into a wall it could never cross. The oldest objects in the universe stopped glowing in colors we can see. Their light got stretched into something invisible to us. Scientists call it infrared. You already know it as the warmth you feel from a campfire before your hand ever touches the flames. James Webb was built to see that hidden warmth. Its instruments chill down to nearly the coldest temperature that can exist, close to -400 degrees. It has to be frozen. A warm telescope would glow with its own body heat and blind itself, like trying to spot a single candle while standing inside a burning oven. So the whole telescope hides behind a sunshield the size of a tennis court, blocking the sun, the earth, and the moon at the same time. Here is the payoff. Infrared light slips straight through the thick clouds of cosmic dust that stop ordinary light cold. Stars are born inside those clouds. Entire galaxies hide behind them. Hubble saw the curtain. James Webb sees what waits behind it. And there is one more trick, the strangest of all. Because light needs time to travel, staring far into space means staring back into the past. This telescope was designed to look so far that it could catch light from the first galaxies that ever formed, light that left them more than 13 billion years ago. That glow has been racing toward us since before the sun, the earth, or a single living cell existed. For the team that built it, the first real image was a moment of pure terror. They aimed humanity's greatest eye at a tiny, dark, seemingly empty patch of sky, a spot so small you could hide it behind a grain of sand held at arm's length. They expected almost nothing, a few faint smudges. If they were lucky, then the picture loaded onto their screens. What they saw broke their models. It contradicted their math. It stunned everyone standing in the room. That single image was about to trigger a crisis in science that still has no ending. Before we step into that first image, you need to understand the wildest thing about it. When James Webb looks deep into space, it is looking backward through time. And once that idea clicks in your head, the universe stops feeling so safe. Light is fast, almost unimaginably so. It crosses the whole distance from the sun to your face in about 8 minutes. So when you look up at the sun, you never see it as it is right now. You see it as it looked 8 minutes ago. If the sun blinked out this instant, you would keep feeling its warmth for 8 more minutes, unaware. Now stretch that idea. The next closest star is so far away that its light takes more than 4 years to reach you. Look at it tonight, and you see light that left it years ago. Push further, out to other galaxies, and the numbers explode. Light from some galaxies has been traveling for millions of years. Light from the farthest ones has been traveling for billions. So the deeper James Webb stares, the further into the past it sees. Point it at something 13 billion light years away, and you are watching a scene that played out 13 billion years ago. You are seeing a baby picture of the universe, frozen in the light that finally arrived. The telescope is a time machine that only points one direction, backward, but there is a twist, and it is the key to everything that follows. The universe is not sitting still, it is expanding every day. The space between galaxies stretches wider, like the skin of a balloon slowly blowing up with dots drawn all over it. As that space stretches, it drags the light traveling through it, and it stretches the light too. Picture the sound of a race car. As the car speeds away, its engine drops to a lower pitch. Light does something similar. When light gets stretched by the expanding universe, it slides toward the red end of the rainbow. Astronomers call this shift redshift. The more the universe has stretched during the light's journey, the redder that light becomes by the time it lands in the telescope. Here is why that matters for you. The very oldest light has been traveling the longest, so it has been stretched the most. It gets pulled so far that it leaves visible colors behind entirely and turns into infrared, that invisible warmth we talked about. Ordinary telescopes go blind to it. James Webb was built for exactly this. It reads redshift like a fingerprint. The redder the object, the older and more distant it usually is. That single measurement is how scientists prove how far back they are truly seeing. They spread a galaxy's light into a spectrum, like a rainbow smeared across a screen, and they hunt for specific lines that act as markers. By measuring how far those markers have slid toward red, they can calculate the galaxy's distance and its age with shocking precision. This is confirmed science, tested and retested for more than 100 years. Astronomers trust this ruler more than almost any other tool they own. So when James Webb captured that first crowded image and measured the redshifts hidden inside it, the team could tell exactly how far back they were peering. The answer landed like a punch to the gut. Some of that light came from a time when the universe should have still been almost empty. And that is where the trouble truly began. So let us finally step into that first image, the one that made a room full of grown scientists go quiet. In July of 2022, the team released it to the world. They had aimed James Webb at a speck of sky near a distant cluster of galaxies. The exposure took less than a single day, and when all that light gathered, the tiny black speck lit up with more than 7,000 galaxies, scattered across the frame like glitter spilled on black paper. Remember how small this patch was. Hold a grain of sand at arm's length, up toward the night sky. The bit of sky it covers is roughly what James Webb photographed. In that one grain of sand's worth of darkness, thousands of galaxies waited, each holding billions of stars. Multiply that across the entire sky, and the number of galaxies climbs into the trillions. Your brain cannot really hold that number. Nobody's can. But the shock was more than the crowd. It was where some of those galaxies sat in time. When the team measured the redshifts, a handful of faint red smudges turned out to be almost unbelievably far away. Their light had traveled for more than 13 billion years. That meant the telescope was seeing them as they looked only a few 100 million years after the universe began. In cosmic terms, that is the delivery room. The universe was a newborn, still wet behind the ears. And these newborn galaxies looked wrong. Scientists had a careful story for how the first galaxies grew. In that story, the early universe was a thin, cold soup of hydrogen and helium gas. Gravity slowly pulled the gas into clumps. The clumps slowly lit their first stars. Small galaxies formed first, then merged over billions of years into the giants we see today, slow and steady, small to large. That was the plan the entire field believed. The galaxies in the image refused to follow the plan. Some of them shone far too bright. Brightness usually means lots of stars, and lots of stars means lots of mass. These early galaxies seemed to hold far more mass than any slow, gentle story could build in such a short time. It was like opening a nursery and finding toddlers who could already run marathons. At first, many astronomers assumed it was a mistake. Maybe the distances were wrong. Maybe closer galaxies were faking the signal, glowing red for some ordinary reason. That would be the boring answer. And boring answers are usually the correct ones in science. So teams around the world raced to check. They spread the light of these galaxies into spectra, hunting for those redshift markers. One by one, the distances held up. The galaxies really were that far. They really were that old. And they really were that big and that bright. That is when the mood in the field changed. A few strange objects can be flukes, but James Webb kept finding them. Image after image, field after field. The early universe already blazed with bright, growing galaxies, far sooner than anyone had dared predict. Astronomers started using a word they almost never say out loud: impossible. And the deeper the telescope looked, the more impossible things it found, because the true scale of the problem was still hiding, waiting in the very next batch of data. Here is the true size of the problem, and it dwarfs a single weird galaxy. Before James Webb launched, astronomers wrote down their predictions. This is how honest science works. You say what you expect to see, then you look, so nobody can fool themselves afterward. Their models predicted that bright galaxies in the first few 100 million years should be extremely rare, faint, tiny, and spread so thin that the telescope might catch only a lucky few, and only after staring for dozens of hours at a single spot. Then James Webb looked, and it found those early bright galaxies almost everywhere. The telescope turned up roughly 100 times more of them than the models had predicted. 100 times is enormous. A miss that large usually means something in the recipe is deeply wrong. Picture ordering enough pizza for a birthday party of 10 kids, then opening your front door to find 1,000 hungry guests crowding your lawn. That is the gap between what scientists expected and what the sky actually delivered. So what went wrong? Astronomers have a few suspects, and this part is still an open fight. The first idea is simple. Maybe the early universe built stars faster and more efficiently than we thought. In our galaxy today, star formation is messy and wasteful. Gas collapses, a few stars ignite, and their fierce winds and explosions blow the leftover gas away before it can build more. It is like striking a match in a strong wind. Most of your fuel scatters before it can catch. But if the early universe was calmer or packed more tightly, maybe those first clouds burned almost all their gas straight into stars. More stars means more light and brighter galaxies sooner. The second idea is stranger. Maybe the first stars were monsters. Some scientists think the earliest stars could grow hundreds of times heavier than our sun. Giant stars burn blue and blinding, thousands of times brighter than ordinary ones. A galaxy stuffed with these giants would look enormously bright, while actually holding far fewer stars than we assume. The brightness would be a trick of the light. The third idea is the scary one. Maybe our whole timeline is off. Maybe galaxies started forming earlier than the models allow, which would mean something about the early universe, or even about gravity and the mysterious dark matter, works differently than the textbooks claim. Right now, nobody knows which answer is correct. It could easily be a blend of all three. Teams are testing each one, and every few months new data tips the argument back and forth. This is a living mystery, unfolding while you watch. But whatever the cause, the basic fact has survived years of hard checking. The early universe was far more productive than we believed. It was making light, making stars, and building structure at a speed that keeps embarrassing our finest predictions. And this is only the wide view, the whole crowd seen from far back. Scientists wanted the record. They wanted the single most distant galaxy of all, the current edge of everything we can see. So they pushed James Webb to its absolute limit. When they finally found that edge and measured it, The object staring back at them was even more troubling than the crowd. So astronomers went hunting for the edge, the single most distant galaxy anyone could confirm. To find it, a team aimed James Webb at one patch of sky and stared for a punishing stretch of time, soaking up the faintest trickle of ancient light they could gather. They found a small red smudge, nothing dramatic to look at. A little banana-shaped blob, half bluish and half deep red, tucked right beside a brighter, closer galaxy. You would scroll straight past it, but when the team spread its light into a spectrum and measured the redshift, the room went electric. This galaxy sits so far away that its light took about 13,400,000,000 years to reach us. We see it as it looked when the whole universe was only 290 million years old. Try to feel that. Squeeze all of cosmic history into a single year, with the Big Bang on January 1st and today on New Year's Eve. This galaxy shines from around the 6th of January. The universe was 6 days into its life. For a while, this smudge held the crown as the most distant galaxy ever confirmed. Scientists tagged it with a long code of letters and numbers that no human wants to say out loud, so let us just call it the record breaker. And the record breaker should have been a faint little nothing, a loose clump of a few young stars, barely clinging together. That is exactly what the old models promised for anything this early. The universe had barely started. There had been almost no time to build. The real thing shattered that expectation. It glowed with the light of hundreds of millions of suns. When astronomers measured its width, it stretched more than 1,000 light years across. To picture how absurd that is, remember that light is the fastest thing there is, and it still takes over 1,000 years to cross this baby galaxy from one side to the other. Something had already assembled a real, sprawling galaxy here, at full speed, in a slice of time the universe was barely supposed to allow. That should have been impossible on its own. A galaxy this big, this bright, this early, cooked up in a few 100 million years, when the gentle old story needed billions. So astronomers did what good scientists always do when a result seems too wild. They tried to kill it. Maybe the distance was wrong. Maybe a closer, dustier galaxy was faking that red glow. Teams checked the spectrum again and again, hunting for any ordinary explanation that would let everyone relax and go home. The result held. The distance was real, the size was real, the brightness was real. This truly was a grown-up galaxy staring back from the universe's first week. That alone rewrote textbooks. A mature galaxy, fully built, in the first few 100 million years of everything. Astronomers thought they had found the ultimate edge, the oldest light they would ever measure. They were wrong about that too. Out in the same deep data, an even fainter, even older glow was waiting. And when a team finally locked onto it, the edge of everything moved once more, back toward a moment when the universe should have been almost pure darkness. The new champion arrived in 2025, and it beat the old record by only 10 million years. In a human life, 10 million years would swallow all of history 1,000 times over. In the life of the universe, it is a paper-thin sliver. Yet that sliver dragged astronomers into ground they thought was unreachable. This galaxy shines from just 280 million years after the Big Bang. Back on our one-year calendar of all time, its light comes from around the 5th of January. The universe was 5 days old, barely awake, still forming its very first structures. Finding it was brutal. The light had been stretched so far, faded so much, and aged so deeply that below a certain color the galaxy simply disappears. It shows up only in the deepest infrared, the exact range James Webb was built to capture. Astronomers measured its spectrum, found the telltale markers sliding toward red, and confirmed the distance. The visible edge of the universe had jumped again, and this champion wore the same troubling face as the last one. It was bright, it was compact, its light squeezed into a tight, dense knot, far smaller than a grown galaxy. Whatever built it worked fast and packed everything in tight. To fit that much light into so small a space, this galaxy had to be forming stars, at a blistering rate, hammering them out far quicker than any calm, gradual model would ever allow. Here is the part that turned a single oddity into a genuine crisis. This champion had company. Once astronomers knew what to look for, they kept finding galaxies like it, again and again, in the earliest sliver of time. By now, they have confirmed dozens of bright galaxies from the universe's first few 100 million years. One strange galaxy is a fluke you can shrug off. Dozens is a pattern you cannot. So the pattern is locked in, checked by many teams, published and defended. The early universe was already stuffed with bright, compact, fully working galaxies, far sooner and in far greater numbers than any model allowed. The size problem is real. The speed problem is real. But size and speed turned out to be the easy part, because when astronomers stopped asking how big these galaxies were and started asking what they were built from, the mystery went from strange to almost unbelievable. Every galaxy you have ever seen, including our own, is made of more than just hydrogen and helium. It is salted with heavier stuff: oxygen, carbon, nitrogen, iron, the very atoms that make up rocks, water, air, and you. Those heavier atoms take time to create. A lot of time. They can only be forged in the hearts of stars, and only released when those stars die. So finding them inside a galaxy means that galaxy has already lived through at least one full cycle of stars being born and burning out. When scientists measured the chemistry inside these first galaxies, they found those heavier atoms already there. In a universe only a few days old, on our cosmic calendar, the ashes of dead stars were already drifting through the gas. And the very first heavy element they pinned down, inside the oldest galaxy of all, was the same one keeping you alive right now. The element was oxygen, the same gas filling your lungs on every single breath you take. Let us be clear about where oxygen comes from, because this is the whole point. The Big Bang was a lousy chemist. When the universe was born, it made almost nothing but the two simplest gases, hydrogen and helium, and little else. For a long stretch, the entire universe was just those two light gases, and nothing heavier existed anywhere. Every atom of oxygen in existence was built later, inside stars. A star spends its life crushing light atoms together in its core, fusing them into heavier ones, step by step. Deep inside, hydrogen becomes helium, helium becomes carbon, carbon climbs toward oxygen, but the star hoards all of it, locked away in its center. The only way to set those new atoms free is for the star to die, often in a violent explosion that scatters its guts across space. That wreckage seeds the next generation. It is how the universe slowly, over ages, grows richer and heavier. That process is slow. It needs stars to form, to live out their lives, and to die. And that is exactly why finding oxygen in the oldest galaxy of all hit astronomers so hard. To find it, they used a second giant observatory down on Earth, a vast array of dishes high in the Chilean desert, to back up what James Webb had seen. They tuned it to catch the exact fingerprint that oxygen leaves in light. And there, in a galaxy from when the universe was under 300 million years old, that fingerprint showed up clear and strong. This claim was so bold that scientists braced for it to crumble. A result this shocking gets attacked from every side, which is exactly how it should be. So two separate teams dug into the data on their own, working apart, using different methods. Both teams found the oxygen. The signal was real, and there was a sharper twist. The galaxy held far more than a faint trace. It carried roughly 10 times more heavy elements than anyone had predicted for something so young. This was a galaxy already well-stocked, already chemically mature, sitting in a universe that had barely had time to make its very first stars. Sit with what that means. To salt a galaxy with that much oxygen, whole generations of stars had to be born, burn through their fuel, and blow themselves apart, all before this snapshot was taken. And this snapshot comes from the universe's first few days on our year-long calendar. The cosmic clock simply does not seem to have enough hours in it for all of that to happen. This is confirmed, measured, double-checked science. The distance is real. The oxygen is real. The strange richness is real. All of it clashes with the timeline we carried in with us. For over a century, scientists built a careful, gentle story of how the universe assembled itself, slowly and patiently, from simple gas into rich galaxies. That single oxygen signal drove a crack straight through the middle of it. And oxygen was only the beginning of the chemistry problem. When astronomers looked harder, they found other heavy elements too, in amounts and mixtures that pointed at something even wilder happening among the very first stars. To really feel why this breaks people's brains, we need to talk about time, specifically how long it takes to salt a galaxy with heavy atoms. Start with a single big star. Massive stars live fast and die young. One of them might shine for only a few million years before running out of fuel and blowing apart. In cosmic terms, that is a blink. So the dying part can happen fairly quickly. Good so far. But dying is only one step. Before a star can die, it has to be born. And before it can be born, cold gas has to gather, clump, and collapse under its own gravity until it grows hot enough to ignite. That gathering takes time. Then, after the star explodes and flings its fresh atoms into space, that enriched gas has to slow down, cool off, and pull back together to build the next generation. That takes time too. Each loop of the cycle costs millions of years, stacked on top of millions more. Now line all of that up against the budget. The oldest galaxies we have found are only 200 to 300 million years old. Inside that tiny window, the universe had to cool from the Big Bang, gather its first gas, light its first stars, let those stars die, spread their ashes, gather that enriched gas again, and build a bright, chemically rich galaxy out of it. Maybe more than once. It is like watching a time lapse of a forest. Normally you would see a bare field, then seedlings, then young trees, then a tall old forest, over hundreds of years. What James Webb showed us looks like a full-grown forest appearing in a couple of weeks. The steps are the same. The speed makes no sense. So how did the early universe run its assembly line so fast? Astronomers are chasing a few possibilities, and this is an active, unfinished argument. One idea is that the very first stars were enormous, far bigger than the stars around us today. Giant stars burn through their fuel in a flash and die almost immediately, pumping out heavy atoms at breakneck speed. A galaxy full of giants could enrich itself far faster than a galaxy of ordinary stars. Another idea is that everything in the early universe was simply packed closer together. Space had not expanded much yet, so gas was denser, gravity acted quicker, and stars formed in tighter, faster bursts. A crowded room lights up faster than an empty stadium. Whatever the cause, the raw fact stands, confirmed and repeated. The early universe built heavy chemistry at a speed our theories struggle to explain. It ran the same story of stars living and dying that our own galaxy ran, yet somehow crammed it into a fraction of the time. That should feel personal, by the way. Every atom of oxygen in your blood, every bit of carbon in your bones, was forged inside dying stars like these. James Webb is watching the earliest chapters of the exact process that eventually built you. It is our own origin story, playing out faster than we ever thought was possible. And when scientists identified the other elements hiding in these galaxies, the clue pointed straight at those giant first stars, and toward a kind of star nobody has ever actually seen. The next elements astronomers found were nitrogen and carbon. On their own, they might sound ordinary. Nitrogen fills most of the air you breathe. Carbon is the backbone of every living thing, but the amounts and the mix told a strange story. In some of these early galaxies, the balance of elements looked off. There was surprisingly heavy nitrogen compared to everything else, far more than our normal models of star chemistry would produce. It was like baking a cake and finding way too much of one spice, in a ratio that a regular kitchen would never create by accident. That odd flavor is a clue. It hints that strange, unfamiliar stars cooked these atoms, rather than the calm suns we know today. The leading suspect is a special class of star that astronomers have long predicted yet never directly confirmed. Scientists call them the first stars. They were the very first suns ever to shine, born from pure hydrogen and helium, with no heavy elements mixed into them at all. That pure starting material changes everything. In stars today, tiny amounts of heavy atoms act like a thermostat, helping the gas cool and stopping it from clumping too big. The first stars had no such break. With nothing to cool the gas, it could pile up into truly monstrous stars, some possibly hundreds of times heavier than our sun. Picture the difference between a candle flame and a blowtorch. Same basic fire, wildly different scale. These giants would have lived hard and died fast, some lasting only a couple of million years before detonating. Their deaths were titanic explosions that flooded their galaxies with fresh, heavy elements in almost no time. That would explain the impossible speed. It would explain the strange chemical mix. It would explain how a galaxy could grow rich and mature while the universe was still a newborn. There is one catch, and it is a big one. Nobody has ever caught a clear, confirmed image of these first stars. They are a prediction, a piece of theory that fits the clues beautifully, but still waits for direct proof. The unusual chemistry James Webb keeps finding may be the closest evidence yet that these giants truly existed. Astronomers are hunting hard for a direct sighting, and finding one would be a landmark moment in all of science. Step back and look at the whole picture, because it is getting serious now. One scientist described a growing chasm between our theories and what the telescope keeps showing us. Every deep look turns up galaxies that are too big, too bright, too rich, and too fast for the careful story we built over 100 years. The gap between prediction and reality keeps getting wider every year. That is unsettling in the best possible way. It usually means we are standing right on the edge of a breakthrough. When the universe refuses to match the textbook this often, the textbook is the thing that changes. Somewhere in this pile of impossible galaxies may be the clue that rewrites how we think everything began. But so far, we have been looking at whole galaxies, enormous cities of stars. Tucked inside, this same early data was something far smaller and far stranger. A tiny red point that shone like a giant, refused every category we had, and left even veteran astronomers admitting they had no idea what they were looking at. Astronomers gave them a name that sounds almost harmless: the little red dots. That gentle name hides a serious headache. As James Webb swept across the young universe, the same odd object kept appearing in image after image. A tiny point of light, sharp and small, glowing a deep, intense red. First, there were a few, then dozens, then hundreds. By 2025, scientists had catalogued more than 300 of them, scattered through the early cosmos like red freckles across a face. The name is blunt for a reason. In the raw images, they truly look like nothing more than tiny red points. Each one is a single pinprick of crimson light, with no arms and no sweeping shape, so small and so red that every telescope before James Webb missed them completely. They had been hiding out there the whole time, waiting for an eye that could finally see infrared. Now, here is the first thing that makes no sense. These dots are tiny, yet each one blazes with the brightness of a whole galaxy. Something is cramming a galaxy's worth of light into a space that looks absurdly small. Imagine walking down your street and spotting a single porch light that somehow shines as bright as an entire city skyline. You would freeze. You would stare. That is what these dots did to the people studying them. They also showed up at a very specific time and then bowed out. The little red dots begin appearing around 600 million years after the Big Bang. They thrive for a stretch of cosmic time, filling the deep images. Then they fade away, mostly vanishing from the record by the time the universe reaches about 1.5 billion years old. They arrive, they flourish, and they leave, almost as if the young universe went through a phase. For a class of object this common, you would expect scientists to know exactly what they are. Astronomers have understood bright, distant, glowing things for decades. There were really only two categories to sort them into, and every bright object we knew of dropped neatly into one or the other. The first category is a galaxy packed with stars. Enough stars burning together can light up the dark across billions of miles and shine all the way to us. Simple enough. The second category is a feeding black hole. When a giant black hole sits at the center of a galaxy and pulls in gas, that gas swirls, heats up, and glows ferociously before it falls in. These blazing feeders are among the brightest single objects in the universe. Also simple enough. For years, almost everything bright and far away fit into one of those two boxes, stars or a feeding black hole. Astronomers assumed the little red dots would settle into one box or the other once they gathered enough data. The dots refused both. Every time scientists tried to force a red dot into the star box, something broke. Every time they tried the black hole box, something else broke. These tiny crimson points were behaving like nothing else in the entire catalogue of known objects. That is when a few astronomers, only half joking, started saying the little red dots had broken cosmology, and the more closely they studied the light pouring off these things, the deeper the trouble got. To understand why the dots broke both boxes, you have to look at their light the way a scientist does. When astronomers spread a dot's glow into a spectrum, smearing it out like a rainbow across a screen, they saw a shape that stopped them cold. The light made a V. It was bright at the blue, ultraviolet end. Then it dropped down, dim through the middle. Then it climbed back up, glowing strong at the red end. Bright, dim, bright again. A clean V, over and over, in dot after dot. That V shape is the heart of the mystery, because a normal galaxy full of stars does not make that pattern, and a plain feeding black hole does not make it either. The light looks like two very different things blended into one signal, and squeezing that exact blend out of a single ordinary object turns out to be extremely hard. Push on the star explanation, and it collapses under its own weight. To make a red dot this bright using only stars, you would have to pack a galaxy's worth of stars into a space unbelievably small. The stars would sit so tightly crushed together that the density becomes almost physically ridiculous, far beyond anything ever seen in any galaxy across the sky. The numbers just break. So astronomers turn to the feeding black hole idea, which handles the brightness much more easily. A black hole gorging on gas can shine that fiercely from a tiny region with no trouble at all. For a while, that looked like the answer. Then someone checked the other kinds of light. A feeding black hole is a loud, messy eater. As it rips gas apart, it should scream in powerful X-rays, a specific signal that observatories are built to catch. So scientists pointed X-ray telescopes at the dots and waited for the scream. The dots stayed quiet, eerily, wrongly quiet, in exactly the way a hungry black hole never should be. The X-rays that should have come pouring out simply were not there. That silence knocked the simple black hole idea off balance just as badly as the star idea had collapsed. So picture the corner astronomers were backed into. The dots are far too bright and far too small to be an ordinary cluster of stars. They are far too quiet in X-rays to be an ordinary feeding black hole. Yet there they sit, hundreds of them, glowing with that same stubborn V-shaped light all through the early universe. This is why the field got so loud. Some researchers argued the dots had to be strange, super dense clumps of stars. Others insisted they had to be black holes, hidden behind thick shrouds that swallow the X-rays. Papers flew back and forth. Conferences turned into shouting matches. For a stretch, the little red dots were one of the hottest arguments in all of astronomy, and a huge part of that argument is still unsettled right now. And there was one more clue that made the dots even harder to explain, a clue hiding in time itself. These objects do not only puzzle us with how they look, they puzzle us with how they leave. Because after flooding the early universe, the the little red dots do something that no one has fully explained. They vanish. Here is the clue that makes the little red dots feel almost eerie. They do not last, and their disappearance is a puzzle all its own. For one stretch of early cosmic time, they are everywhere. Deep image after deep image turns up more of them, hundreds of tiny red points sprinkled across the young universe. Then, as the universe ages past roughly 1.5 billion years, they thin out and fade from the record. Look at the universe today, all around us, and you find almost none of them. Whatever the little red dots were, they were creatures of the early cosmos, and they left. A whole class of object appearing, dominating, and then nearly disappearing is a serious clue. Things in space usually do not just evaporate. So where did they go? This is one of the sharpest questions in the whole mystery, and astronomers have a few competing answers, none of them fully proven. The first idea is that the dots survived. They grew up. Maybe a little red dot is a snapshot of an early stage, a phase that every young galaxy or young black hole passes through. As time goes on, the object changes, sheds its strange red disguise, and settles into something more familiar, like an ordinary galaxy or a normal glowing black hole. Under this view, the dots simply matured into things we already recognize, so we stopped labeling them as dots. It is like asking where all the caterpillars went when they quietly turned into butterflies. The second idea points to dust and gas. Some scientists think a red dot may be a bright object wrapped in a thick cocoon of gas and dust. That cocoon glows red and hides whatever sits inside. Over time, the object could blow the cocoon away or burn through it, changing how it looks to us entirely. Once the veil lifts, the object stops appearing as a little red dot. The third idea is the boldest. Maybe the dots really do represent a special, one-time event in the young universe, a kind of object that could only form in the crowded, gas-rich conditions of that early era. When those conditions passed, no new dots could form, and the old ones ran their course. Under this view, we are seeing the fingerprints of a chapter of cosmic history that will never repeat. Right now, nobody can say for certain which answer is right. It may even be a blend of them. This part is a genuine open mystery, the kind that keeps scientists awake and arguing late into the night. But solving where the dots went depends on first solving what they are. And on that question, one explanation has slowly pulled ahead of the pack. It is the strangest idea in this entire story so far, and it forces you to picture something that sounds like a flat contradiction. Imagine a star, a giant, glowing ball of hot gas, wider across than our entire solar system. Now imagine that at its very center, instead of the usual nuclear furnace, there sits a black hole, feeding on the gas from the inside out. A star and a black hole fused together into one impossible object. Astronomers call it a black hole star, and it might just be the key to everything. So, what on earth is a black hole star? Let us build one, piece by piece. Start with a black hole. Picture a spot in space where gravity has gone completely out of control, so strong that nothing escapes it, not even light. Drop matter toward it, and the matter puts on a show. It swirls into a searing hot disk first, spinning faster and faster, heating up until it glows with ferocious brightness. A feeding black hole is one of the most powerful light sources in the entire universe. Now wrap that whole thing in a gigantic cloud of gas. Make it dense and thick, a blanket of hydrogen so wide it dwarfs our whole solar system, with the feeding black hole buried deep in the middle. From the outside, you cannot see the black hole at all. You only see the vast, glowing ball of gas around it, lit up from within by the monster at its core. That is a black hole star. From a distance, it looks like a single enormous star, a giant, glowing sphere. Its light comes from the black hole eating gas at the center, rather than from the nuclear furnace that powers a normal star. A star on the outside, a black hole beating at the heart. Here is why this idea excited so many astronomers. It explains the little red dots almost too well. That thick blanket of gas would glow red, matching the deep crimson color of the dots. The gas cocoon would also muffle the X-rays, soaking them up before they could escape, which explains the eerie silence that ruined the plain black hole idea. And a black hole, feeding at full tilt, could easily pump out a galaxy's worth of brightness from a tiny space, which explains how something so small can shine so hard. One object. 4 mysteries solved at once. The color, the tiny size, the crushing brightness, and the missing X-rays. That is the kind of clean fit that makes scientists sit up straight. The evidence has been building fast. Astronomers found specific objects in the James Webb data that show the exact signature you would expect from a giant glowing gas envelope with a hidden power source deep inside. One team even reported catching a black hole star from extremely early in cosmic time, the sort of object that could be the engine hiding inside hundreds of little red dots. A growing group of scientists now leans toward this picture. As one researcher put it, part of the field is starting to agree that black hole stars can explain the little red dots. That is a big shift from the years of pure confusion that came before. Still, honesty matters here. This idea is winning, but it has not fully won. The black hole star is a strong, exciting best guess, and it fits the clues better than anything before it. Yet scientists are careful people, and they want more direct proof before they close the case. Some researchers still push rival explanations, and the debate keeps rolling on. But if you really want to feel how violent and extreme these objects are, you have to look at just one of them up close. Because when astronomers measured the raw power pouring out of a single black hole star, the number they got was so large it barely fits inside the human imagination. Let us zoom all the way in on a single black hole star and measure its raw power. The result is one of the most staggering numbers in this whole story. Astronomers found one of these objects blazing with the light of roughly 100 billion suns. Say that slowly. 100 billion. That is more stars than our entire home galaxy, the Milky Way, contains. And all of that light pours out of one single object hidden behind a shell of gas, glowing from the dawn of time. Try to picture 100 billion of anything. If you count it out loud, one number, every second, never sleeping, never stopping to eat, reaching 100 billion would take you more than 3,000 years. That is the light of a single black hole star, shining across 13 billion years to reach a telescope parked 1 million miles from Earth. So how does one object get that violently bright? The secret is how greedily the black hole at its center feeds. A black hole makes light in a completely different way from a star. A star glows by fusing atoms together in its core. A black hole glows by wrecking things. As gas spirals down toward it, that gas slams and grinds against itself, heating up to temperatures that make the inside of a normal star seem chilly. The superheated gas shrieks with radiation before it vanishes forever. In effect, the black hole is turning raw gravity into pure light, wringing more energy out of every scrap of falling gas than any burning star could ever hope to. The faster the black hole feeds, the more fiercely it shines. And these early black holes feed at a furious, almost reckless pace. There is supposed to be a natural speed limit on how fast a black hole can swallow gas. The idea behind it is neat. As a black hole feeds, the infalling gas blazes with light, and that light pushes outward. Feed too fast, and the outward blast shoves the incoming gas away, choking off the meal like a flame that burns so hot it snuffs out its own fuel supply. That limit is supposed to keep every black hole growing at a slow, orderly rate. Yet the black hole stars seem to smash straight through it. They gulp gas faster than the rule book says is possible, and they blaze all the harder for it. Somehow, in the crowded, gas-drenched early universe, these monsters found a way to eat past the point where they should have choked. That reckless feeding explains the blinding light. It also does something far more troubling. A black hole that eats this fast grows fast, swelling in size at a pace that should not be possible. Feeding is how a black hole gains weight, and these were feeding like nothing we see anywhere today. So astronomers did the obvious thing. They put these early black holes on the scale, weighed the galaxies wrapped around them, and compared the two numbers. What came back broke a rule that scientists had trusted for decades, a rule so steady that most of them treated it as a plain fact of nature. To feel why that result was such a shock, you first need to understand the rule it shattered. Almost every big galaxy has a giant black hole sitting at its center, including our own, and across the nearby universe, astronomers noticed a remarkably tidy relationship between the two. The central black hole always carries about the same small fraction of its galaxy's total weight, roughly 1 part in 1,000. Picture the galaxy as a sprawling mansion, and the black hole as a single heavy safe tucked into one room. Big mansion, slightly bigger safe. Small mansion, slightly smaller safe. The safe is always about the same tiny slice of the whole house. That ratio held up across galaxy after galaxy after galaxy, so reliably that scientists treated it almost like a law of nature. Wherever you looked in the modern universe, the safe stayed politely small. Then James Webb weighed the black holes in the early universe, and the tidy rule fell to pieces. These young black holes were massively overweight for their galaxies. Instead of 1 part in 1,000, some of them carried 10 or even 100 times more of their galaxy's mass than they should. In a few jaw-dropping cases, a single black hole weighed nearly as much as all the stars in its galaxy put together. The safe was suddenly as heavy as the entire mansion around it. Astronomers named these misfits the overmassive black holes, and they are a genuine headache because they flip our whole story of how galaxies and black holes grow up together. For a long time, scientists assumed a galaxy and its central black hole grew side by side, hand in hand, like two trees planted in the same soil on the same day. The galaxy pulls in gas and builds stars. The black hole feeds on some of that same gas and grows in step, slow and balanced, both rising together, which is why their weights stay locked in that neat ratio in the universe we see today. The overmassive black holes tell a completely different story. They suggest that, in the early universe, the black hole got a giant head start, ballooning to enormous size, while its galaxy was still small, thin, and half-built. The safe showed up long before anyone had finished building the mansion around it. That reverses the order everyone expected, and it hints that black holes may come first, with the galaxies catching up later. This finding is confirmed, checked by many separate teams using careful measurements of the light from these galaxies. Again and again, they land on the same answer. The black holes really are too heavy. The pattern is solid, even though the reason behind it is still fiercely argued over. There is one honest twist worth mentioning. A few researchers suspect that some of these black holes only look heavier than they truly are. If a small black hole is feeding at that reckless, over-the-limit pace, its fierce glow can fool our instruments into overestimating its size. So part of the puzzle might be an illusion born of extreme feeding. That would ease the problem a little, though it would not make it vanish, because plenty of these giants still look stubbornly, genuinely huge. Whatever the final verdict, the core shock stands. In the young universe, black holes were already colossal, sometimes rivaling everything around them, at a time when they simply should not have been able to grow so big. And that impossible size raises the single hardest black hole question James Webb has forced upon us. Here is the question that keeps black hole scientists up at night. How do you grow a black hole to 1 billion times the weight of the Sun when the universe is only a few 100 million years old? To see the trap, follow how a black hole actually gains weight. It grows by feeding. Gas falls in, and the black hole gets heavier. There is no other way for it to bulk up. So, the size of a black hole is really a story about time. The bigger you want it, the longer it has to sit there and eat. Now start the clock with a normal black hole, the kind left behind when a big star dies. That starter weighs maybe 10 times our Sun. Feed it, and it grows. But black holes do not gain weight in a straight, steady line. They grow by doubling. 10 becomes 20, 20 becomes 40, 40 becomes 80. Each doubling takes a certain minimum stretch of time, set by that feeding speed limit we met earlier. And to climb from 10 suns all the way up to 1 billion, you need an awful lot of doublings, stacked one after another. Do the arithmetic, and it falls apart. Even feeding at the fastest steady rate the rules allow, without ever pausing, that chain of doublings takes longer than the entire age of the early universe we are looking at. The clock you would need runs out before the black hole comes anywhere near 1 billion suns. There simply are not enough hours between the Big Bang and the snapshot James Webb captured. Yet the giant black holes are right there, staring back at us from that impossibly early time. Confirmed, measured, enormous. So one of our assumptions has to give way. Scientists are chasing two main escape routes, and the fight between them is one of the liveliest arguments in astronomy. The first route is the reckless feeding we already saw. If early black holes could smash past the normal speed limit and gorge far faster than the ceiling allows, even in short, violent bursts, they could pile on weight much quicker than the gentle math predicts. The black hole stars hint that this kind of over-the-limit feeding really did happen. This could shrink the time problem, though many scientists doubt it can fully solve it on its own. The second route is bolder and stranger. What if these black holes never started small in the first place? What if, instead of beginning life as the tiny corpse of a single dead star, they were born already gigantic, skipping the slow starter stage completely? A black hole that begins its life weighing thousands or tens of thousands of suns has a colossal head start. Give it that, and suddenly there is enough time on the clock to reach 1 billion. That second idea is the one gaining serious ground. It flips the whole origin story of black holes upside down, and it points toward a birth process unlike anything happening in the universe today, a way to forge a massive black hole in a single dramatic step, without ever building a normal star first. It sounds extreme. It might also be exactly what happened, and it carries us straight into one of the wildest ideas in all of modern astronomy. The wildest idea has a name: direct collapse, and it might be how the universe cheated to build its first giant black holes. To understand it, remember the normal way a black hole is born. A big star lives its life, runs out of fuel, and dies in a colossal explosion. Whatever remains collapses into a black hole, but that black hole starts small, only a few times the weight of the sun, because a single star can hold only so much mass. That is the slow starter we just watched fail the time test. It begins far too tiny to ever reach 1 billion suns before the clock runs out. Direct collapse throws out the star completely. Instead of waiting for a star to form, live, and die, you take a gigantic cloud of gas and make it fall together all at once, straight into a black hole in a single dramatic step. The whole cloud crushes itself into a black hole that is born already massive, thousands or even tens of thousands of times the weight of our sun, right from the start. Hand the early universe a fleet of these fat, newborn black holes, and the time problem melts away. They begin with a huge head start, so they have plenty of time to feed their way up to 1 billion suns before the cosmic clock runs out. The impossible suddenly looks reachable. But direct collapse only works under very picky conditions, and this is where it gets delicate. To crush a giant gas cloud straight into a black hole, you have to stop it from breaking into smaller pieces and forming ordinary stars along the way. Normally, a big cloud cools, fragments, and shatters into many small stars. That is how star clusters are born. To get a direct collapse instead, the gas has to stay hot and smooth, refusing to clump, so the whole thing can drop together as one massive unit. That needs a special environment, the kind that may have existed only in rare pockets of the young universe. So is direct collapse confirmed? Not yet. This is a leading theory, a strong contender. backed by careful computer simulations that show it could work. But nobody has directly watched a black hole being born this way. It stays one of our best explanations for a real problem, and scientists are hunting hard for solid proof. And here the threads of this whole story suddenly tie together. Remember the little red dots and their hidden black hole stars? Some scientists now suspect those very objects might be direct collapse, black holes caught in the act, freshly born giants wrapped in thick cocoons of gas, feeding hard and glowing red. If that is right, then the little red dots could be far more than a curiosity. They could be our front row seat to the birth of the first giant black holes. Stack it all up, and the picture is staggering. In the first few 100 million years, the young universe was already building enormous galaxies, cooking heavy elements, and forging giant black holes, all far faster than our finest theories said was possible. Every deep look confirms it, and every answer we find seems to crack open two brand new questions. The universe grew up in a terrible hurry, and we are still fighting to understand how. But the strangeness does not stop with galaxies and black holes, because when James Webb turned its eye toward the shapes of these early galaxies, what it found was stranger than anyone was ready for. The first surprise in the shapes was a spiral, a giant, perfect pinwheel of stars spinning in a place and time where it had no business existing. Astronomers were studying a bright, distant object when they noticed a large galaxy sitting in the same patch of sky. At first, the lead scientist thought it was a nuisance, some ordinary galaxy from nearby that had wandered into the shot and gotten in the way. He almost ignored it. Then he measured how far away it truly was, and everything changed. This spiral, nicknamed the Big Wheel, sits so far off that its light took about 12 billion years to reach us. We are seeing it as it looked when the universe was only 2 billion years old, roughly 15% of its current age, and it is enormous. Its spinning disk of stars stretches more than 100,000 light-years across, making it the largest spiral ever confirmed from that early era. It holds around 5 times as many stars as our entire Milky Way, packed into a disk that covers twice the area. Take a second to feel how wrong that is. A spiral galaxy is a delicate thing. Those graceful arms are a pattern, and patterns are fragile. In the crowded early universe, galaxies were constantly crashing into each other. Every collision should scramble a spiral into a shapeless blob, the way stirring a spoon through swirled cream in your coffee erases the swirl in seconds. So a young universe should be full of messy, half-built galaxies, still colliding and churning. A clean, giant spiral this early should have been impossible. It is like watching a demolition derby and spotting one car cruising through the chaos with a perfect, unscratched paint job. Yet the Big Wheel is exactly that. It grew to a monstrous size and still kept its elegant spiral arms and its smooth, orderly spin. It rotates as fast and as neatly as the biggest spirals in the universe today, the fully grown ones that had billions of extra years to settle down. How did it pull that off? The best clue is where it lives. The Big Wheel sits in an unusually crowded corner of the early universe, a region packed about 10 times denser with galaxies and gas than normal space. Astronomers think all that surrounding material may have fed the galaxy in a smooth, steady flow, letting it bulk up fast without the violent, spiral-wrecking collisions that usually come with rapid growth. A rare, gentle feast instead of a brawl. That idea is still being tested, and the Big Wheel might simply be a freak, a 1 in 1,000 accident of a perfect environment. The team behind it even estimated they had less than a 2% chance of stumbling across such an object at all. One scientist compared finding it to spotting a living dinosaur, a creature from an age when it should already be extinct. Rare or not, the Big Wheel proves something unsettling. The early universe could build a colossal, mature, beautifully ordered galaxy far faster than our models allow. Nature found a shortcut we still cannot explain. And if you think one giant spiral is strange, wait until you meet the galaxy that looks like a mirror image of our own home, appearing even earlier and looking even more finished than it had any right to be. 2 astronomers in India were combing through James Webb images when they found it. A spiral galaxy so much like the Milky Way that it could pass for our twin. They named it Alaknanda, after a Himalayan river, because in Hindi, the Milky Way itself carries a river's name. Alaknanda is the real shock of the two spirals, and here is why. It appears when the universe was only about 1.5 billion years old, even younger than the Big Wheel, and it does not look like a rough, early sketch of a galaxy. It shows the full, textbook design that we thought took many billions of years to draw. Picture the classic shape of the Milky Way, a bright, rounded bulge of stars in the middle, with two clean, sweeping arms curling out from the center in a graceful, balanced spiral. Scientists call this a grand design spiral, and it is the gold standard of galactic beauty, rare and hard to build even today. Alaknanda has all of it, two symmetric arms wrapped around a glowing central bulge, spanning about 30,000 light-years, a smaller and tidier cousin of our own galaxy. Most spiral galaxies have ragged, patchy arms. A true grand design, with two clean arms sweeping symmetrically from the core, is the rarest and most striking layout of all, and it usually marks a galaxy that has enjoyed a long, calm life to perfect its shape. Now stack that against what the models predicted. Early galaxies were supposed to be lumpy, disorganized, and clumpy, still fighting their way toward any real shape. Finding a finished grand design spiral this early is like walking through a brand new city where every building is still a construction site, then turning a corner and finding one gleaming skyscraper already complete, furnished, and full of light. And Alaknanda is doing something furious inside. It is forming new stars at roughly 20 times the rate of the modern Milky Way, cranking out fresh suns worth about 60 times the mass of our own sun every single year. Even wilder, astronomers found that about half of all its stars formed in a span of just 200 million years. In cosmic terms, that is a lightning-fast burst of creation, a galaxy assembling most of itself almost overnight. Astronomers were able to study it in this much detail thanks to a lucky trick of gravity, which bent and magnified its faint light on the way to us. We will come back to that trick later, because it becomes the key to something even more extreme. For now, hold on to what Alaknanda means. It is one of the clearest, most orderly spiral galaxies ever seen from that young an age, and it currently holds the record as the most distant grand design spiral we know. It's stitched together roughly 10 billion suns worth of stars and organized them into a smooth, spinning disk in just a few 100 million years. The people who found it said plainly that it forces us to rethink how galaxies come together. Two beautiful spirals, both far too grand, far too soon. So how does our theory of galaxy building actually work? And why do these spirals break it so badly? To see the problem clearly, you have to understand the recipe astronomers thought every galaxy followed. To see why these spirals rattled astronomers, you have to understand the recipe scientists believed every galaxy followed. It is a bottom-up recipe, built from small pieces into big ones over a very long time. In this picture, the universe starts with tiny clumps of gas and dark matter. These small clumps pull on each other, drift together, and merge. Little galaxies crash and combine into medium ones. Medium ones combine into large ones. Over billions of years, galaxies grow the way a snowball grows, rolling downhill, gathering everything in their path. Scientists call this hierarchical growth, and it is the backbone of how we thought all structure formed. Now here is the catch. That building process is violent. Every merger is a collision, and collisions stir everything up. To make a smooth, flat, spinning spiral, a galaxy needs the opposite of chaos. It needs calm. All its stars and gas have to settle into one thin, tidy plane, orbiting together in the same direction, like sand settling flat and still at the bottom of a jar long after you stop shaking it. That settling takes time, and it takes peace. So the models predicted that flat, orderly spiral disks should appear late, only after the wild merging era had mostly finished, once galaxies finally had a few billion quiet years to calm down and flatten out. Early galaxies were supposed to be thick, puffy, and turbulent, still getting slammed from every side. The Big Wheel and Alaknanda tear a hole in that timeline. They are thin, flat, spinning, and beautifully ordered, at a time when the universe should have been too rough to allow it. And they have company. Since James Webb switched on, astronomers have found a surprising number of orderly disk galaxies in the early universe, far more than the old recipe predicted. What looked like two freak accidents is starting to look like a pattern. So how do scientists explain it? This is where the argument heats up, and there are a few serious ideas on the table. The first idea says the disks were fed gently. Instead of growing only through violent mergers, some early galaxies may have grown by drinking in smooth, steady streams of cold gas flowing straight from the space around them. A calm diet like that could build a big disk quickly without wrecking its shape. The second idea says disks can settle faster than we thought. Under the dense conditions of the early universe, gravity may have organized these galaxies into flat, spinning shapes in a fraction of the expected time. The third idea is more careful, and it keeps everyone honest. Maybe we are only seeing the rare winners, the handful of galaxies lucky enough to stay calm, while the messy majority hides in plain sight. Our eyes get drawn to the pretty spirals, fooling us into thinking they are more common than they really are. Right now, no single answer has won. The debate is loud and unfinished, and that is exactly how a real scientific mystery sounds. What is clear is that the early universe could build order far faster than the textbook allowed. But order is only half the story, because for every graceful spiral James Webb found, it also found galaxies that look like something went horribly, spectacularly wrong. Turn away from the tidy spirals, and most of the early universe looks like a disaster zone. When James Webb surveyed thousands of young galaxies, the majority were rough and unfinished. They were lumpy, stretched, and broken, like blobs of clay squeezed by a careless hand. Astronomers had actually expected this part. Remember, the old recipe said early galaxies should be messy while they were still assembling. And James Webb delivered plenty of mess. It found galaxies shaped like tadpoles, with a bright head and a long straggly tail. It found galaxies that looked like chains of glowing beads. It found others that resembled train wrecks frozen mid-crash, with clumps of stars scattered in every direction and no center to speak of. Some of these galaxies are so shapeless that they barely qualify as a shape at all. They are giant, glowing knots of gas and newborn stars, still slamming together, still deciding what they want to become. If you saw one next to the Milky Way, you might not even believe they were the same kind of object. So far, so expected. The strange part is the contrast. In the very same era, in the very same slices of cosmic time, the universe was somehow producing both extremes at once. On one side, flawless grand spirals like Alaknanda. On the other, chaotic wrecks that looked like they were assembled in a blender. Two wildly different outcomes, side by side, in a universe barely old enough to make either. No single, simple model predicted both at the same moment. A cosmos that can craft a flawless spiral should not also be flooded with wreckage. And yet here both sit together in the same snapshot. That contrast is the real clue. It tells astronomers that galaxy building in the early universe was wildly uneven. In some rare, calm corners, gravity spun up smooth, orderly disks with shocking speed. In most other places, galaxies grew in a frenzy of collisions, staying rough and jumbled for a long time. The same young cosmos ran two completely different construction projects at once. There is another twist buried in these messy galaxies. When astronomers look closely at the lumps inside them, those clumps are often furiously forming stars, blazing with the light of brand new suns. A single bright knot inside one of these train wreck galaxies can outshine an entire normal galaxy. The chaos hides a firestorm of creation, pumping out stars at a furious pace, and that connects back to a puzzle we have already met. All these violent, clumpy, colliding galaxies are exactly the kind of environment that could churn out heavy elements fast, could feed young black holes at reckless speeds, and could pile up mass quicker than the gentle models allow. The mess and the impossibilities may be two sides of the same coin. For now, picture the early universe as a place of extremes: perfect order in a few spots, total chaos nearly everywhere else. Both far more advanced, far more active, and far more surprising than anyone predicted before James Webb opened its eye. But the universe had a shock waiting that flips this whole story around, because James Webb also found early galaxies doing the one thing nobody thought was possible so soon. They had already stopped. They were finished. They were, in a very real sense, dead. A dead galaxy sounds like a strange idea, so let us be clear about what it means. A living galaxy makes new stars. It pulls in gas, collapses it, and lights fresh suns over and over. A dead galaxy has stopped. Its star-making has switched off, and all it has left are the stars it already built, slowly aging and reddening like coals dimming after a fire burns down. Astronomers call these quiet, finished galaxies quenched. In the universe around us today, dead galaxies are common. They are the old retirees of the cosmos, galaxies that ran their course over many billions of years, used up or lost their gas, and settled into a long, calm old age. That is the normal story. Galaxies live fast and young, then slow down and quiet over enormous stretches of time. So imagine the surprise when James Webb found galaxies that were already dead when the universe was still a baby. The telescope spotted galaxies that had shut down their star formation just 1 billion years or so after the Big Bang, some even earlier. These galaxies had already lived their whole active lives, built up their stars, and then switched off, all inside a window where most galaxies were supposed to be just getting started. Finding them is like walking into a kindergarten and meeting a child who has already retired. Sit with how much has to happen for that to be true. To be dead this early, a galaxy first had to be born, then form a huge population of stars in a blazing hurry, then run out of fuel or blow it all away, and then go quiet, all before the cosmic clock had barely started ticking. It crammed an entire lifetime, birth to death, into a sliver of time when other galaxies had not even finished being born. These early dead galaxies also tend to be surprisingly massive. Many are packed with as many stars as a large modern galaxy, meaning they built an enormous amount of mass and then slammed on the brakes. The building was fast. The shutdown was fast. Everything about them is fast. How does a galaxy die so young? Scientists have a few suspects, and this is still an open question. One idea is that a galaxy formed stars so violently that its own exploding stars and stellar winds blasted all the leftover gas out into space, starving itself of the fuel it needed to keep going. It burned so hard that it snuffed itself out. Another idea points to a giant black hole at the center. When one of those monsters feeds and roars, it can heat and blow away the surrounding gas, shutting down star birth across the whole galaxy. The very black holes we met earlier could be the assassins here. Whatever the cause, these dead galaxies deepen the crisis in a sharp new way. It is one thing for the early universe to build galaxies too fast. It is another for it to build them, run them, and finish them, all in record time. And that raises a question stranger than anything we have asked yet. Why would a quiet, dead galaxy be even harder to explain than a bright, blazing one? The answer flips our whole sense of what should be difficult. Here is the twist that makes dead galaxies so unsettling. A quiet, finished galaxy in the early universe is actually harder to explain than a bright, active one. And once you see why, the whole puzzle sharpens. Think about what a bright, blazing early galaxy needs. It needs to form stars fast. That is one impressive trick, one hard thing to pull off. Astronomers can at least imagine ways to speed up star birth, like denser gas or bigger stars. A galaxy that shines is a galaxy caught in the middle of doing one amazing thing. A dead galaxy has to pull off two amazing things in a row, back to back, with no time to spare. First, it must build all its stars in a furious sprint, matching the same impossible speed as the brightest early galaxies. Then it must slam the brakes and shut everything down almost immediately after. Two extreme events, both crammed into the same tiny window. The galaxy has to sprint at full speed, then stop dead in the blink of a cosmic eye. Two separate miracles, stacked one on top of the other, both crammed into the universe's opening moments. Picture a runner in a race. Building stars fast is like sprinting at world record pace. Now imagine that same runner hitting top speed, then freezing completely still in a single step without stumbling or slowing. That sudden, total stop is its own separate miracle. A dead early galaxy did both at once, and it did them when the universe had barely begun. There is a second reason these galaxies are so strange. To go quiet, a galaxy has to get rid of its gas, or heat it up so much that it can no longer collapse into stars. Gas is the fuel of galaxies, and the early universe was drowning in it. Fresh gas was everywhere, constantly raining down onto young galaxies, feeding them. So an early galaxy that managed to stay dead had to somehow fight off that endless rain of fuel, keeping itself starved even while the universe kept trying to feed it. That is like bailing water out of a leaking boat, except the leak never stops and the sea keeps pouring back in. That takes real power. To shut down and stay shut down, something inside these galaxies had to push back hard against all that infalling gas. The leading suspect, again, is a giant central black hole, blasting out enough energy to hold the gas at bay. If that is right, then these dead galaxies are more evidence that huge, powerful black holes were already up and running in the first billion years, shaping and even killing their host galaxies. So the dead galaxies tie the whole story together. They demand impossible speed, the same speed that shocked us in the bright galaxies. They demand a sudden, violent shutdown, and they point straight back at the early giant black holes we have been chasing this whole time. Every thread keeps leading to the same uncomfortable truth. The early universe did everything too fast. It lit up too fast, grew too fast, enriched itself too fast, and even died too fast. And James Webb was about to catch the ultimate example of early violence. A moment of pure cosmic chaos on a scale that stunned even the scientists who study collisions for a living. Most galaxy collisions involve two galaxies, sometimes three, drifting together and slowly merging. James Webb found 5 of them, smashing into each other at once. Only 800 million years after the Big Bang, astronomers nicknamed it the Quintet. 5 separate galaxies, caught in the act of crashing together in one tight, chaotic knot of space, at a time when the universe was barely old enough to have built 5 galaxies close enough to collide. Collisions this crowded are staggeringly rare. Even in today's universe, where galaxies have had billions of years to drift into each other, mergers of this many galaxies at once make up far less than 1 in 100. To find one this early, in the universe's first billion years, borders on winning a cosmic lottery. Picture the scene: 5 galaxies, each holding countless stars and vast clouds of gas, all falling toward the same point, their gravity yanking them into a violent pileup. Streams of stars get torn loose, gas clouds slam together and ignite. The whole system blazes as the crash triggers a firestorm of new star birth. Together, these 5 galaxies are forming new stars at around 250 times the rate of the modern Milky Way. It is one of the most violent, productive events in the early universe ever caught on camera. Why does a 5-way crash matter so much? Because collisions like this are how the biggest galaxies in the universe get built. Our own Milky Way grew, in part, by swallowing smaller galaxies over billions of years. Mergers are the engine of galaxy growth. Finding a 5-galaxy merger this early means that engine was already running at full throttle when the universe was a tiny fraction of its current age. the building of giant galaxies started far sooner than the models expected. Whatever machinery assembles the largest galaxies in the cosmos was clearly already switched on and running hard. There is a strong hint about this system's future too. All that furious star formation burns through gas at a reckless rate. Astronomers think the quintet may quickly exhaust its fuel, merge into a single large galaxy, and then go quiet. Put another way, this violent crash could be caught in the very act of creating one of those impossible early dead galaxies we just talked about. We might be watching the birth of a corpse. That connection is what makes the quintet so valuable. It ties the wild, colliding chaos of the early universe directly to the finished, quenched giants that shocked us. The crash builds the mass in a frenzy. The frenzy burns the fuel. The galaxy goes dead. A whole cosmic life cycle, sped up and squeezed into the universe's opening act. Astronomers found this system inside one of the deepest images James Webb has ever taken, a long, patient stare into a single patch of sky. And the closer they looked at the quintet, the more they realized the crash had done something to the space around it. Something was leaking out of these galaxies and spreading into the void between them. What they found floating in that empty space should not have been there at all. It was a clue about how the early universe spread the ingredients of life itself, far and wide, long before anyone thought it could. The empty space between galaxies is supposed to be just that, empty, a vast, dark, near-perfect vacuum. So when astronomers studied the quintet, they were stunned to find a glowing halo of gas stretching through the space around and between the 5 colliding galaxies. And this gas carried a fingerprint that changed everything. It was rich in oxygen, the same heavy element we chased through the earliest galaxies, along with other atoms forged inside stars. Heavy elements like oxygen are born deep in the hearts of stars and scattered when those stars die. Finding them out in the open space between galaxies means those atoms had already been flung far beyond the galaxies that made them. Why is that such a big deal? Think about where heavy elements usually stay. A star cooks them in its core. When it dies, it spreads them into its home galaxy. For those atoms to travel further, all the way out into the void between galaxies, something has to physically throw them there. And doing that in the universe's first billion years, when galaxies had barely finished forming, was supposed to be impossible. The quintet shows exactly how it happened. As the 5 galaxies crash together, their gravity rips long streams of gas out of each other and slings that enriched material into the surrounding space. The collision itself acts like a giant slingshot, hurling the products of dead stars far beyond their birthplaces. Picture a food fight, where the mess does not stay on the plates. It ends up splattered across the walls, the floor, the whole room. The gas the astronomers spotted was that splatter, caught in the act, glowing faintly across the long, dark corridors between the 5 galaxies. Before James Webb, astronomers thought this kind of widespread seeding took much longer to get going, that the space between galaxies stayed clean and empty until well over 1 billion years after the Big Bang. The glowing, oxygen-rich halo around the quintet proves the seeding started far earlier, driven by these violent early collisions. This matters more than it might sound, because those scattered heavy atoms are the raw material for everything that comes later. The oxygen you breathe, the calcium in your bones, the iron in your blood, all of it began as heavy elements forged in stars and spread across space, generation after generation, mixing into new clouds that formed new stars, and, eventually, planets and people. James Webb is watching the earliest, most violent chapters of that great scattering, the slow process that turned a bland universe of hydrogen and helium into one rich enough to build worlds. The quintet, then, is more than a rare crash. It is a snapshot of the early universe learning to spread the ingredients of life, flinging them out into the dark far sooner than we believed. Every collision like it made the cosmos a little richer, a little more ready for what would come billions of years later. But heavy elements were not the only thing showing up too early and in the wrong places. James Webb kept finding another ingredient scattered through the young cosmos, one so ordinary on Earth that you wipe it off your shelves, yet so puzzling in the early universe that it became a crisis all its own. The ingredient is dust, ordinary cosmic dust, the same kind of fine, sooty grains that drift through space everywhere. On Earth, dust is boring. In the early universe, it turned into a genuine headache. First, understand what cosmic dust actually is. Cosmic dust is tiny grains of solid material, things like carbon and silicon, floating between the stars. These grains are the raw building blocks of planets, and even of you, since the rocky Earth beneath your feet is basically dust that clumped together over billions of years. Dust matters. It is where solid worlds begin. Every planet, every moon, every patch of solid ground in the cosmos traces back to grains of this stuff. Here is the problem. Dust is made by stars, and mostly by old ones. Certain aging stars puff out grains of dust in their final stages, gently seeding space with the stuff. Dying stars also forge it in their explosions. Either way, making a lot of dust normally takes time, because you have to wait for whole generations of stars to grow old and die first. So, a very young galaxy should be nearly dust-free. It has not had time to grow old stars, so it has not had time to make much dust. That was the clear expectation. James Webb, along with its partner telescopes, found the opposite. Peering at galaxies from the first billion years, astronomers detected surprising amounts of dust, far more than such young galaxies should be able to produce. One scientist summed up the puzzle simply. These galaxies seem too young for the amount of dust they contain, because they do not have enough old stars to have made it. It is like walking into a brand new house, one built just last week, and finding the attic already packed with dusty old cobwebs. The dust has no business being there yet. Something made it far faster than the normal, slow process allows. This is a real, confirmed detection. Astronomers even spotted a specific fingerprint in the light, a particular signature that certain kinds of dust grains leave behind, showing up in galaxies from deep in cosmic time. The dust is truly there. The open question is how the young universe built so much of it so fast. There are a few ideas. One says, the first massive stars, the giant ones that live and die in a flash, could have forged dust in their violent deaths at high speed, skipping the slow route entirely. Another points to special hot, fast-burning stars that shed material quickly. In this view, the early universe had a dust factory running on fast forward, cranking out grains through the rapid deaths of enormous stars. Whatever the source, the dust problem stacks neatly on top of everything else. Too many galaxies, too big, too bright, too rich in heavy elements, and now too dusty. The same pattern over and over. The early universe did more and did it faster than our models can comfortably explain. But dust had one more surprise hidden inside it, because when astronomers looked even closer, they found a possible escape hatch, a clever trick of physics that might make the dust problem far less impossible than it first appeared. And for once, the universe might actually be letting us off the hook. The escape hatch comes down to a single clever idea. Warm dust can fool you. A small amount of hot dust can shine just as brightly as a huge amount of cold dust, and that changes everything about the problem. Here is the trick. When astronomers measure dust in a distant galaxy, they cannot count the grains one by one. What they measure is the glow. Dust soaks up starlight and then re-radiates it, giving off a warm infrared shine. The brighter that shine, the more dust everyone assumed must be there. But brightness depends on two things at once. It depends on how much dust there is, and on how hot that dust is. Cold dust glows faintly, so you need a giant pile of it to make a strong signal. Hot dust glows fiercely, so even a small pinch of it can blaze just as bright. A single glowing coal can throw off as much light as a whole heap of cooler ash. This is the loophole. When James Webb and its partner observatories studied certain early galaxies, they found the dust in them was warm, heated by the intense starlight of galaxies that were forming stars in a frenzy. And warm dust is deceptive. A galaxy might look like it is stuffed with dust, drowning in the stuff, when really it holds only a modest amount that happens to be glowing hot and bright. Astronomers studied one galaxy from about 600 million years after the Big Bang that showed exactly this. It glowed a fierce red from heated dust, looking alarmingly dusty for its young age. But the warmth of that dust meant the galaxy needed far less of it than the raw brightness suggested. The dust was hot, so a little went a long way. Suddenly, the numbers looked much less impossible. What had seemed like a mountain of dust turned out to be a modest sprinkle, glowing far above its weight. A crisis that was partly a trick of temperature all along. That single insight takes a lot of pressure off the dust crisis. If many early galaxies are hiding modest amounts of hot, bright dust rather than mountains of cold dust, then the young universe never had to build as much as we feared. The problem shrinks to something the normal, faster-dying stars could plausibly manage. This is how science is supposed to work, and it is worth pausing on. A shocking result appears. It looks impossible. Then, instead of throwing out all of physics, researchers dig deeper and sometimes find that a subtle detail, like the temperature of dust, was quietly skewing the measurement all along. The universe was following the rules the whole time. We were simply reading the evidence a little wrong. It is a healthy reminder. Many early universe puzzles turn out to have ordinary answers. Some, on closer inspection, melt away into clever explanations. The dust may well turn out to be one of those, but other puzzles refuse to melt. And James Webb had just turned up a haul of 300 objects so bright, so massive, and so early that no simple loophole could easily explain them away. If even a few of them are what they appear to be, they could crack the story wide open. The 300 objects came from a team at the University of Missouri, digging through some of the deepest infrared images James Webb has ever captured. Scattered across those images, they found 300 points of light that, by every measure they could take, should not be shining so brightly. To hunt for the oldest objects, astronomers use a clever technique built on redshift, the stretching of light we talked about early on. As light travels across the expanding universe for billions of years, it stretches toward the red, and the very oldest light gets pushed so far that it drops out of the bluer filters entirely and shows up only in the reddest, most infrared ones. So astronomers look for objects that vanish in the blue filters but light up in the red. An object playing that particular game of hide and seek across colors is almost certainly extremely far away, and therefore extremely old. 300 objects passed that test, marking them as candidates from the deep early universe. And that is where the trouble started. When the team estimated how bright these objects truly are, the numbers came back far too high. Galaxies forming this soon after the Big Bang are supposed to be faint, limited by how few stars they have had time to build. These 300 blaze far brighter than the models say anything that early has any right to. The word candidates matters here, and the scientists are careful to stress it. These objects have been spotted and measured, but they still await full confirmation. To lock down exactly how far away each one is, astronomers need to spread its light into a detailed spectrum, a slow and demanding follow-up. Until that happens, there is still a chance that some of them are nearer, more ordinary objects wearing a convincing disguise, fooling the color test. That caution is important, and it is honest science, but the sheer number is what makes this exciting. Finding one or two impossibly bright, early objects could be a fluke or a measurement error. Finding 300 of them, all at once, in a single survey, is much harder to wave away. Even if most turn out to be ordinary, the scientists point out that if only a handful are truly what they appear to be, that alone could challenge our whole picture of how galaxies formed. Think about the pattern building here. We started with a first image that held too many galaxies, then came galaxies too big and too bright, then chemistry too rich, then black holes too heavy, then spirals too orderly. then galaxies dead too soon, and now 300 more objects glowing too fiercely, too early, waiting to either be explained away or to blow the timeline apart. Each new discovery on its own might be dismissed. Together, they pile into something that is getting very hard to ignore. The early universe keeps refusing to be as quiet and simple as we expected. To settle it, astronomers need to see these objects in far greater detail to pull apart their light and read their true distances and natures. And that quest, the drive to zoom in on the faintest, most distant specks of all, leads to one of the most jaw-dropping tricks in all of astronomy, a way to use the universe itself as a giant magnifying glass. The trick uses gravity itself as a lens, and it lets us see things that should be far too small and faint for any telescope, even James Webb, to catch. Here is the idea. Anything with mass bends the space around it, and light has to follow those bends. So when a huge clump of mass, like a giant cluster of galaxies, sits between us and something far behind it, the cluster's gravity bends and focuses the light passing by. Exactly like a glass lens, the distant object behind it appears stretched, smeared, and, most importantly, magnified. Nature builds a telescope in the sky, one far larger than anything humans could ever launch. Astronomers call this gravitational lensing, and it is confirmed, rock-solid physics, predicted by Einstein over a century ago and seen countless times since. When the alignment is just right, a lucky background galaxy can be magnified by hundreds or even thousands of times. It is like holding a magnifying glass up to the deepest, most distant corners of the universe. And in one perfect alignment, this cosmic magnifying glass did something almost unbelievable. It let astronomers see a single star, all the way back in the early universe. That should sink in. Individual stars in distant galaxies are normally impossible to pick out. A far-off galaxy is just a smudge, its billions of stars blurred into one faint glow. Seeing one single star among them, across billions of light years, is like trying to spot one particular firefly blinking in a city viewed from a passing airplane. It cannot be done except through a fluke of gravity. For decades, catching a single distant star this way was only a dream. Then the universe lined up two objects across billions of light years with almost impossible precision, and the dream came true. The star earned the nickname Arundel, an old word meaning morning star. A massive galaxy cluster sat perfectly in front of it, and a sharp ripple in that cluster's lens magnified Arundel by a factor of at least a few thousand, maybe far more. That magnification lifted a single star out of the blur and made it visible. Its light took nearly 13 billion years to reach us, meaning we see it as it shone in the universe's first billion years. When James Webb studied Arundel, it found a giant. The star is more than twice as hot as our sun and shines about 1 million times brighter. It may even have a companion star orbiting alongside it. Astronomers are careful to call it a candidate, because at these distances, telling one star from a tight cluster of a few stars is genuinely hard, and the debate is ongoing. Still, it stands as the most distant single star ever spotted, a lighthouse from the dawn of everything. Arundel is thrilling on its own, but it hints at something bigger. If gravity can magnify one ancient star into view, then maybe, with the right alignment, it could reveal an even older, even more important kind of star. A star from the very first generation ever born, a type astronomers have chased for decades and never confirmed. That would be the ultimate prize. And the hunt for it is one of the great unfinished quests in all of science. We met these first stars earlier as the giant suspects behind the strange chemistry of the young universe. Now let us face the biggest embarrassment in all of this. After all its discoveries, James Webb has still never confirmed a single one of them. Astronomers call them Population 3, a clumsy name for the most important stars that ever existed. They were the first suns, the ones that switched on when the universe had never known starlight. Before them, the cosmos was a dark, cold sea of hydrogen and helium, waiting in total blackness for its first light. These stars ended that darkness. They lit the first fires and forged the first heavy atoms, seeding everything that followed. Every star you can name, every galaxy in every image, every atom of oxygen and iron and carbon, traces back to these first stars and their descendants. They are the true beginning of the visible universe, and we have never seen one for certain. Why are they so hard to find? A few reasons pile up. First, they were among the earliest things to exist, so their light is the most stretched, the most faded, the most buried in distance. Second, they burned out fast. The giant first stars may have lived only a couple of million years before exploding, a flicker in cosmic time, so the window to catch them shining is painfully narrow. Third, they were rare and scattered, single points of light in an ocean of dark. Finding one is a true needle in a haystack, except the haystack is the size of the observable universe, and the needle winked out of existence more than 13 billion years ago. So astronomers get creative. Their best hope is the gravity lens trick we just saw with Arundel. If a first star, or a small cluster of them, happened to sit behind a perfectly aligned galaxy cluster, the magnification could lift its ancient light into view. Teams are actively scanning the skies for exactly this, hunting for the telltale signs of a pure, primitive star with no heavy elements inside it, glowing from the very edge of time. There have been tantalizing hints. Now and then, a distant galaxy shows traces of the strange chemistry you would expect if a pocket of first stars lived inside it. A few candidates have made headlines, but every time, the evidence stays just short of proof, a whisper rather than a shout. The first stars remain a prediction, beautifully supported by everything around them, yet never caught in the act, confirming even one would be a landmark for the ages. It would let us finally test our ideas about how giant those first stars really were, how they lived, how they died, and how they kindled the chemistry that eventually built planets and people. It would connect us directly to the very first light in existence. Until then, the first stars stay a ghost, haunting the edge of every deep image, always just out of reach. James Webb was partly built to catch them, and the chase is far from over. And that unfinished chase points at the deepest question of all, because the first stars did more than shine. They flipped a switch that transformed the entire universe. And the timing of that great change is turning into one of the sharpest problems James Webb has raised. The switch the first stars flipped is called reionization, and it changed the entire universe from a dark fog into the transparent cosmos we live in today. The trouble is, James Webb suggests it happened too fast, powered by more light than the early universe should have been able to make. Let me paint the picture. For a few 100 million years after the Big Bang, the universe was filled with a thick fog of cold hydrogen gas. This fog was murky. It trapped light, scattering and blocking it, so the young cosmos sat dark and hidden behind a haze. Astronomers call this stretch the cosmic dark ages, and it was exactly that, dark. Then the first stars and galaxies switched on. They flooded space with intense ultraviolet light, and that light did something dramatic to the fog. It broke the hydrogen apart, splitting the gas into charged pieces that no longer blocked light. Bit by bit, the fog cleared. Bubbles of transparent space opened up around the first galaxies, grew, and finally merged until the whole universe turned clear. Picture sunrise, burning the mist off a lake at dawn, only on a scale spanning all of creation. That great clearing is reionization, and it is confirmed to have happened. We can see its aftermath everywhere. The dispute is about the timing and the fuel. To clear that vast fog, you need an enormous flood of ultraviolet light, a huge number of light particles pouring out of early stars and galaxies. And when astronomers add up all the light sources they can find in the young universe, they keep hitting a wall. The clearing seems to have happened faster and earlier than the known light sources can easily account for. Some studies call it a photon budget problem. There may simply not be enough light in the standard story to burn away the fog as quickly as the evidence shows it vanished. We even caught a glimpse of this earlier, in one of those record-breaking baby galaxies that had already blown a clear bubble around itself. far sooner than expected. That single galaxy was a hint. The full reionization picture turns that hint into a pattern. The universe cleared its fog ahead of schedule, as if someone sped up the sunrise. So what is going on? The answers circle back to everything we have seen. Maybe the early universe made far more stars, and far brighter ones, than we counted, which fits all those too bright galaxies. Maybe the little red dots and early black holes pumped out extra radiation that helped clear the fog. Or maybe our models of how light escapes from these young galaxies are simply wrong, and far more of it leaked out into space than we assumed. Each of these fixes patches the problem in a different way, and astronomers are testing them right now. This is a live, unsettled question, one of the sharpest in the field, and it feeds directly into the biggest question of all. Because when you add up the whole list, the two bright galaxies, the two heavy black holes, the two orderly spirals, the two fast reionization, you have to start asking whether the problem is the universe or whether the problem is us. Whether our entire model of the cosmos might be missing something huge. So here is the question every one of these discoveries has been circling. Is our standard model of the universe starting to crack? First, let us be fair to that model because it has been spectacularly successful. Scientists call it the standard model of cosmology. It describes a universe that began in a hot Big Bang, expanded and cooled, and grew its structure with the help of two mysterious ingredients, dark matter and dark energy. This model predicted the faint afterglow of the Big Bang, the way galaxies cluster across the sky, and the overall shape of cosmic history, all with stunning accuracy. It is one of the great achievements of human thought. Any replacement would have to match all of that success and then some. Now, here is the tension. James Webb keeps finding things in the early universe that this model did not obviously predict. Galaxies too big and bright too soon, black holes too heavy too fast, a fog that cleared too quickly. To a few scientists, this smells like a real crisis, a sign that the model is fundamentally incomplete and that we may need brand new physics to explain the early universe. But most cosmologists urge caution, and their reasoning is important. A shocking observation does not automatically break a theory. History is full of results that looked impossible at first, then turned out to have ordinary explanations once scientists understood their instruments and assumptions better. The dust puzzle we walked through is a perfect example. It looked impossible until a closer look at warm dust quietly diffused it. So the mainstream view is that the standard model is bending, straining, being pushed hard, yet still standing. In this view, the fixes live inside the model itself. Maybe the early universe simply formed stars far more efficiently than we assumed. Maybe some of those blindingly bright objects are feeding black holes, fooling our measurements. Maybe selection effects make the weird galaxies look more common than they are, because strange, bright things are the easiest ones to spot. Each of these tweaks could ease the tension without tearing up the foundations. And there is real progress on this front. Recent studies have shown that several of the scariest early results can be squeezed back inside the standard model with clever, careful adjustments. The bright galaxies are real, confirmed by detailed spectra, but a growing number of astronomers argue they do not, on their own, overthrow the big picture. They stretch it hard. They have not yet snapped it. A smaller group of researchers disagrees and is exploring bolder ideas, entire alternative models that would rewrite parts of cosmic history. So far, none of those alternatives can match the standard model's full track record, its ability to explain the Big Bang's afterglow and everything since. That is a very high bar, and it is why most scientists are still not ready to abandon what works. What everyone agrees on is this: James Webb has forced the most vigorous rethinking of early cosmic history in decades. The debate is loud, healthy, and unfinished. Whether the ending is a patched-up standard model or a whole new picture, we are living through one of the most exciting stretches in the history of astronomy. which leaves us with one final dizzying possibility. The one scientists whisper about when the tensions pile too high. What if the thing we have wrong is time itself? Every puzzle in this story shares one phrase: too soon. Galaxies too big, too soon. Black holes too heavy, too soon. Spirals, chemistry, dust, dead galaxies, all arriving too soon. So, a few bold scientists ask a wild question. What if nothing is actually too soon? What if we have the clock wrong? Think about what would happen if the early universe had more time than we think. Every impossible thing on our list needs one thing above all else: time. Time to build big galaxies, to grow giant black holes, to cook heavy elements, to settle spiral arms, to live and die. If the young universe secretly had more time to work with than our models allow, then suddenly nothing is impossible. Everything simply had room to happen. The whole crisis would dissolve in a heartbeat, traded away for one single, staggering revision to our understanding of time. This is a radical idea, and it is worth being honest about its status. It sits at the edge of mainstream science, far from its settled center. A handful of researchers have proposed alternative theories where cosmic time behaves differently in the early universe, stretching the earliest eras longer than the standard model says. In those theories, the first billion years might really have lasted much longer, giving galaxies and black holes the extra ages they seem to need. Most cosmologists are deeply skeptical of these ideas, and for good reason. Rewriting the flow of time is an enormous claim, and any such theory has to explain the James Webb surprises, and everything else we have ever measured too, without breaking a single piece of it. So far, none has cleared that bar. These remain fringe proposals, fascinating to think about, far from proven, and treated with heavy caution by the wider field. But the very fact that serious people are willing to whisper about it tells you how deep the strangeness runs. When observation after observation keeps pointing the same direction, scientists are forced to question even their most basic assumptions, even the ticking of the cosmic clock. Step back now and look at the whole journey. A telescope 1 million miles from Earth, staring into the dark, sent back a picture that broke its maker's expectations. And discovery by discovery, it has shown us an early universe that is bolder, faster, richer, and stranger than anyone dared imagine. A cosmos that built its first galaxies in a hurry, grew monstrous black holes almost overnight, spun up graceful spirals, forged the ingredients of life, and lit its first fires far sooner than the rules allowed. We do not yet know what it all means. Maybe our models need a few clever repairs. Maybe they need a major overhaul. Maybe, just maybe, our whole sense of cosmic time is due for a rewrite. That uncertainty is the feeling of standing at the exact edge of human knowledge, in the moment before the map gets redrawn. The early universe was hiding something enormous. James Webb pulled back the curtain, and what it revealed is still rewriting the story of where everything, including us, truly came from. The greatest discoveries in this story have almost certainly not arrived yet, and the telescope is still watching, still staring into the deep, waiting for the next impossible thing to appear.